Good morning. I'm M. Yogita from CSMC from Srinivasa Ramanujan Institute of Technology. My topic is classification, impurity versus entropy from machine learning. Introduction to classification. Classification is a supervised learning task where the goal is to assign labels to input data based on patterns. In classification, the output variable is categorical, meaning it belongs to one of a set of predefined classes or groups. It is widely used in applications like spam detection, medical diagnosis, and customer segmentation and image recognition. There are types of classifications: binary classification, multi-class classification, multi-label classification. It is wide. Decision trees are a popular classification algorithms due to interpretability and easy of usage. The effectiveness of decision trees depends on how they split nodes to create homogeneous groups. The choice of splitting criteria impacts the tree structure and accuracy and computational efficiency. Splitting criteria in decision trees. Decision trees recursively split nodes to form homogeneous subsets. The impurity of a node determines whether a split is necessary. Two common impurity measures are used, that is, Gini entropy measures the probability of incorrect classification. Entropy measures the level of disorder and uncertainty in a data set. Low impurity values indicate purer nodes and led to better classification. What is Gini entropy? Gini entropy impurity. What is Gini impurity? Gini impurity is a measure of probability that a randomly chosen element from a dataset which will be incorrectly classified if it is randomly labeled according to the distribution of class labels in the data set. It quantifies how mixed the classes are in a given data set with lower values indicating purer split. Mathematically, it is defined as G is equals to 1 minus sigma I is equals to 1 to C pi square, where G is Gini entropy and C is number of classes, total number of classes. Pi is portion of the class I in the dataset. Gini entropy is a metric used in decision tree like card classification and regression trees to measure how mixed a data set is with respect to class labels. It helps determine how well a split at a node separates the data. If node is pure, Gini entropy is 0. If classes are evenly distributed, Gini impurity is higher. Max is equals to 0.5 for a binary classification with a 50-50 split. Entropy measures the amount of uncertainty or disorder in a dataset used in algorithms like ID3, C4.5 and C5.0. Entropy is equals to minus sigma pi log to pi, where pi is the probability of class I. There are some key properties in the entropy. Non-negative entropy is always greater than or equals to 0. The minimum value is 0, which occurs when all the elements belongs to a single class. Maximum entropy when all classes are equally likely. Entropy is independent of class labels. Only the distribution of probability. Swapping class labels does not change the entropy. If you combine two independent systems, the total entropy is the sum of their individual properties. Small changes in the probability distribution results in small changes in entropy. Entropy is a concave function, meaning the entropy of a mixture is greater than or equal to the average entropy of its parts. Basis of information gain. Entropy is used to compute information gain, which helps in deciding the best attribute to split in decision trees like in ID3 algorithm. Example data set: Here feature 1, feature 2, feature 3 are the some example: sunny, rainy, overcast. In feature 2, hot, cold, mild. Feature 3, no SR class labels is there. Before splitting, the Gini entropy of the given data set is 0.48 and entropy is 0.97. Weighted Gini after split is equals to 0.467. Weighted entropy after split 0.5, 0.951. Information gain, entropy reduction, that is equals to 0.02. Lower impurity values suggest a better split, guiding the decision tree towards more homogeneous classes. Class comparison of Gini entropy and impurity and entropy criteria. Gini impurity, entropy interpretation, probability of misclassification, whereas entropy is a measure of disorder, range 0.0 to 0.5, whereas entropy is 0, 0 to 1. Computation faster, slightly slower due to logarithms. Decision trees used Gini impurity in decision trees used in CAT algorithm, where entropy is used in ID3, C4.5 and C5.0. Sensitivity to class distribution, less sensitive, more sensitive due to small changes. Preference works well in balanced data sets, useful when maximizing information gain. Example: decision tree split. Consider a data set Consider a data set with two classes S or no. Split using Gini calculates impurity and before and after the split, chooses the right chooses the attribute that results in the lowest weighted Gini impurity. Example: if two possible splits give Gini values of 0.25 and 0.32, the algorithm selects 0.25. Split using entropy. Computes the information computes the information gained by comparing entropy before split and after the split. The attribute with the highest information gain is chosen. If two splits results in entropy reduction of 0.5 and 0.3, the first split is preferred. Visualization of decision tree nodes. Show an example tree where a dataset is divided into plural subsets using both methods. When to use Gini versus entropy. Gini impurity preferred when computational efficiency is crucial. Used in chord trees that handle larger data sets, works well in balanced class distributions. Entropy more informative but computationally expensive, sensitive to small changes in data distribution, preferred when maximizing pure information gain is necessary. Practical considerations. In practice, both criteria often yield similar results. Some algorithms default to Gini due to its lower computation cost. Summary: decision trees use splitting criteria to determine the best attribute for classification. Gini impurity and entropy are two common measures to assess node purity. Gini impurity measures misclassification probability and is computationally efficient. Entropy measures disorder and is useful when maximizing data purity. Both methods aim to create purer subsets for better classification performance. The choice between Gini and entropy depends on data size, computational time, and the algorithm used.